Alright, ladies and gentlemen, here we are recording our portion of study on circuit diagrams. And a circuit diagram is just a picture or a circle diagram because circuits are all circles. And circuits, as we stated before, whoops, I went backwards, did not mean to do that. Circles have different elements. So if we come down and click on a pen, we have a voltage source, which are batteries. You have wires, which are conductors, and then resistors that are loads. And resistors are simply devices that take energy out of the battery and convert it into useful forms. This resistor will give off heat. So it might be in your toaster, toasting your toast, or in your electric blanket, keeping you nice and toasty. Or another type of resistor is a light bulb. And we'll draw a light bulb. It would look like that. It will give off energy, not in the infrared or heat, stuff like that. It will give off visible light. So we use symbols to represent these things. We don't draw pictures of resistors like we see here, or batteries like a door cell, and wires. We use symbols to draw pictures, and these pictures that we draw of circles or circuits are called schematics. So we're going to draw a simple circuit that contains a 9-volt battery. I'll just demonstrate so you can see what this process looks like, and then a 3 ohm resistor across its terminals. So we'll start off by drawing a battery, and when we do that, we usually draw one long line and one short one. The long one is positive terminal, the short one is negative, and then we have a conductor which goes up. And we're going to go through a resistor. I'm just going to make a light bulb for our resistor, and we bring it back home. If you prefer, we can label this 9 volts in, 3 ohms of resistance, and we're good to go. So we'll pull out this diagram. There we go. So it's a lot similar to what we just did. Let me see if I can move this out of the way, or I'll make it a little bit smaller. Excuse me, so we can put these side by side. So again, current comes out of the positive terminal, up through the resistor, and then back home, and we have a complete circle. Very nice. Are there a couple ways you can add additional resistors into a circuit? If you look, these resistors, or these circuits, both have 2 resistors, R1 and R2, so you have 2 light bulbs. One way is to put them in a single line, so they're said to be in series. So if I draw, I don't know, I'm going to start off over here and go around this circle. I come up through the battery, and then I come down through the resistor. So these resistors all fall within that same yellow circle. Another way to do it is a parallel circuit. This has multiple paths. So I'll come up through the battery, and then I'm going to go up through R1 and back home. So that's one circle. Notice that this circle does not include R2. That has an independent path. So I'll just grab another color. We'll do it in a color that's not very contrasty. So I come up through the battery, and then down through R2 and back home. So we have 2 different circles. One is yellow and one is that pink color. And that means they have independent paths back to the batteries, and we're good. So all charges must move through both resistors to get to the negative terminal in the case of a series circle. And charges can have 2 ways to travel, either through R1, that top yellow path, or R2, that bottom pink path, but not both. So they have independent or multiple paths. So let's see if we can use this circle process in order to determine if these are a series or parallel. And remember, parallel will have multiple paths. So I'm going to follow this first one. I'm going to go up through the battery, and then I'm going down through this resistor, and I'll bring it back home. So there's one path. Ask yourself the question, is there another path that we could follow? Let's check it out. We'll start off right here. I'll come up through the battery, down through this resistor, and back home. So there's another path. Is that a series or a parallel circuit? Think about that. Multiple paths, parallel. Let's look at the second case. We'll start off here Well, I'm going to go this way. I come up through the battery, down through R2, travel, 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 keep going, and then down through R1. I went through both resistors in a single path. That's a series circuit. So let's reveal this slide and see what they have to say. So we'll move our letters. The test is to trace the shortest route around the circuit. The resistors found on the same route are in series, and those are on different routes or in parallel. So again, we have different routes here, pink and yellow, so we have parallel, and then the same route, just yellow, series. Very nice. Total resistance of a circuit. So when we put multiple resistors in, these resistors impact how much charge can travel through a point in the wire every second, or it influences the current, and it's called Ohm's law. So how much current flows will depend on how much voltage is applied across these resistors and how much total resistance you have. Resistors and voltage from batteries determine the current. Circuits can be redrawn as if there were only a single resistor and battery. By reducing the circuit in this way, the circuit becomes easier to study. And the process of reducing resistors in a circuit is called finding its equivalent, or sometimes they'll call it the total resistance of the circuit. Let's go forward. So if we look at this, what happens to the circuit in the right? I'm going to reveal the answer for this one. Or what happens to the current in the circuit? So we have current traveling in this direction, we have current traveling in this direction, we have a current traveling in this direction, current traveling in this direction, and so on. Now ask yourself, in this case, how many paths are there? The answer is one continuous loop. So the current is said to be king in this, or the current in any location, anywhere within this circle is the same, because there's only one path. So the current here, we'll call that I, would be the current there, maybe I1 in R1, and the current in R2 is I2. Now, let's put this away for a moment. What happens to the voltage in this circuit? And the answer is pretty easy. I'll try and explain. I said this before. When I travel this way, I go up through a battery, and then I continue to go, I travel, and then I come down through these resistors, and if I end up at the same spot, there's no displacement. So that means, just imagine you go up a hill and you come down hills. The sum of your ups is equal to the sum of your downs. If we refer to the voltage across R1 as V1, and we call that one V2, the sum of your ups, V of the battery, would be equal to the sum of your downs. So V equals V1 plus V2, and I everywhere is the same. Now sometimes when I teach this, I'll say in a series circuit, current is king. So we have rules. We know that the voltage of the battery, or what you put in, is the total of what you get out. Since voltage is IR, and the current is the same everywhere, the I's will cancel, and it gives us this new rule: the equivalent, or the total resistance, is the sum of the individual resistances. So the important equations right here and now is that voltage is the sum, the voltage up is the sum of the drops down, and the total resistance in series specifically is the sum of the individual resistors. So the question is, for this problem, what is the total or the equivalent resistance of the circuit? We'll write a formula. R equivalent is R1 plus R2. When we do this, we'll get 5 ohms plus 3 ohms, which will give us a grand total of 8 ohms of resistance. Reveal the slide. There we go. Going to move forward. Now, what is the total current anywhere? We could take this circuit and redraw it. as stated previously, we know that we have 9 volts of potential difference, or a 9-volt battery applied, and then we could redraw this circle or this circuit so it has a single light bulb. And just imagine this single light bulb or this single resistor. Here they're drawing resistors, here I'll draw a light bulb which has resistance, so we can use them interchangeably. This single light bulb would have to have an equivalent resistance of 8 ohms. So to find the current, we'll use Ohm's law. I is V over R, and the voltage applied is 9 volts divided by the resistance, 8 ohms. 9 over 8 is 1 point something and another, 1.125 amps. And what this means is that the current anywhere is always going to be 1.125 amps. So the current there is 1.125 amps. The current there is the same value, 1.125 amps, and so on, the same, and the same, because you only have one path. What are the voltage drops across R1? So let's just restate. If I come up 9, which I went through the battery, I came up 9, I'm going to have to come down and then down again, down through R1 and then down through R2, a total of 9, because the total voltage has to be V1 plus V2, or the voltage of the battery, which is sometimes written just as V, so we're good. Now to find the voltage for 1, we can use Ohm's law. We know that I1 is V1 over R1. When we manipulate, V1 equals I1 times R1. V1 is, I think it was 1.125 amps times that resistance, which is going to be 5 ohms, and that total voltage will be that of the product of those two. We'll cheat, 5.6 volts. Let's move this out of the way. That's going to have to do. Now what is the voltage drop across R2? If we go back here and we write 5.625, we know the voltage here. So the question is, what is V2? If I come up 9, I have to come down, a total of 9. So really, to find out what V2 is, one way to do it is that V is V1 plus V2. Solving for V2, V2 will be V minus V1. I'm going to write, let's just move this up a tiny bit, and we'll sub numbers in. V2, which is the unknown, is V, is that of the battery, 9 minus 5 point, what would we say, 6 volts. When we take the difference of these, I'll save myself the computation, let's reveal it, we get 3.375. 3.375 and 5.625 take us back to 9 volts. Let's use an alternate solution. Finding V2, that would be I2 times R2. V2 is I2, again times R2, just rewrite. V2 is 1.125 amps times what R2 is. Oh, that is 3 ohms. And when we take the product of these two answers, or the current times the resistance, we'll get 3.375. Again, V1 plus V2, 5.625 and 3.375 has to take you back to 9 volts because, let's explain. what you put into the circuit energy-wise is what you get out and out. What goes up must come down. That's all. So if you go uphill, when you come back downhill, you're going to end up back at the same spot. How much power is used by R1? Solving for power, one way to do it, power for 1 is I1 squared times R1. Another way to do it, power 1 is I1 times V1, or power is V squared over R. From the previous parts of the problem, we know everything. I'm going to just use equation number 1. Power 1 is I squared, or I1 squared times R1. So we end up with 1.125 amps quantity squared times what R1 is, 5 ohms. If we do 1.125 squared times 5, you could do this with your calculator yourself. You end up with about 6.33 watts. And that's the meaning of power, or the power output, is that you get 6.33 joules of energy out every 1 second that goes by. So we're on to another problem. What is the equivalent resistance? I'll go fast with this one. Since this is in series, R equivalent is R1 plus R2. R equivalent is 10 ohms plus 20 ohms. R equivalent will be 30 ohms. Let's move forward. So if we consider this to be a big light bulb, it would have a total resistance of 30 ohms and a voltage across that of 9 volts. So to solve for the total current, that's V over R equivalent. That total current would be V, 9 volts, over 30 ohms. So 10 over 30 would be roughly 1/3. So you get about 0.33 amps. Let's reveal the answer. Yeah, 0.3 amps. So 1/3 of an amp. That means 1/3 of a coulomb of charge travels at any point anywhere in this circuit at any point in any time. What is the voltage drop across R1? What is V1 equal to? V1 is I1 times R1. So V1 is I. That's we said 1/3 of an amp, 0.3 amps, close enough, times R1, that's 10 ohms. 1/3 of 10 is a little more than 3 in that ballpark. 3 volts will be good, or 3/10 of 10 is 3. Sorry about that. And so you get 3 volts. Now let's see if we can answer this question together. If the voltage drop across R1 is 3 volts, automatically we would know the voltage over here. I want to remind you, when you come up 9, you have to come down and then down again through a total of 9. So 3 plus some number, whatever that number is for that voltage, has to bring you back to 9. 3 plus what is 9? That's right, the answer is 6 volts. So we could predict this. What would, let's do V2 quickly. V2 will be I2 times R2. So what is 0.3 amps times, oh, I almost made a mistake. Let's erase that resistance for R2. That's 20 ohms. So if I double the resistance given the same current, this was 3 volts. Again, doubling the resistance with the same current will give me double the voltage, 6 volts. 3 and 6 are 9. Beautiful. What is the voltage drop across R2? We just did it, 6 volts. Sorry to do that on the previous slide. I'll just reveal the answer. You can rewind to see that if you need. How much power is used by R1? Power 1 is I1 squared times R1. So power 1 will be 0.3 amps. Don't forget to square it. Quantity squared times R1, which is 10 ohms. 0.3 squared times 10 will reveal the answer is 0.9. Yep. And then lastly, how much power is used by R2? To do that, you could use power for 2 is I2 quantity squared times R2. So this is a square, the superscript is a square, and the subscript just tells me that that's I2. So power 2 is going to be the current, 0.3 amps. That's I2 squared, we're going to square, times R2, 20 ohms. Now in the previous problem, we said the power output is 0.9. If we have the same current, but now we've doubled the resistance, what has to happen to the power output if we double the resistance? If I put a 2 right there where resistance is, if I put a 2 where R is, I'd have to double the power output. So we get 1.8 watts. Again, previously we got 0.9, we get twice as much, 1.8. Alright, in contrast, we have a different type of circuit, parallel circuit, which contains multiple paths. Let's take a look. Let's just use our rule. What happens to the current in the circuit? So we have current traveling, and I'll call that I. So you're putting, I don't know, 10 amps of current there. And then when you reach this point right there, that current comes up, and you reach that point, it's like a fork in the road, it's called a junction. Some of the current will travel in that direction, we'll call that I1, and some of the current will go in that direction, we'll call that I2. And current is a conservable quantity because the matter, the amount of charges you put in, has to be equal to the amount of charges that you get out. And let's just not even call that 10. We'll call that I. So what you put in I has to equal what the sum of what you get out, I1 plus I2. So we'll reveal the answer. What happens to the current on the right? The sum of the currents through each of the resistors in a parallel circuit equals the current of the battery. So that of the branches, I1 and I2, would have to give you the total current. Now, let's put this away for a moment. You can rewind that and pause it to see it. Now the question is, what happens to voltage? If I start here and travel, I come up through some voltage of the battery, we'll call that V. And then when I take this bottom path, I have to come down through R2. So first of all, V will be equal to R2. We'll take a different path. I probably should have taken the first one to go through 1 first, but we'll deal with it. I'll come up through V, and then I go down through R1, and then back home. So what comes up V must come down V through R1, and what comes up V must come down V through R2. So this will give us another rule for parallel circuits. V, the total voltage, or that of the battery, is V1 equals V2. So in a series circuit, which is one path, current would be king, but in a parallel circuit, voltage is king. So we'll reveal and see what they have to say. Let's move that up too. The voltage across resistors in the parallel circuit is the same. V equals V1 equals V2. As you gain confidence in problem solving, this will become second nature, and we'll write down a list of relevant equations at the end of this chapter or at the end of the problem solving related to this that you can refer to, maybe even print out and use. And I'll do that after we solve these parallel circuit problems. These are the easy ones. You're going to do great. So if we look here, there's a set of rules. First of all, current breaks, and then because current here is V over R, we end up with an equation for total resistance is 1 over R. So again, voltage everywhere is the same. That's an important equation. Current everywhere splits, and this is a new and unusual equation that we're going to apply to find the total resistance. What is the total resistance of this circuit? The equation that we're going to apply to find the total resistance is on the previous page, and I'll simply rewrite, or the equivalent resistance. The equivalent resistance is 1 over R1 plus 1 over R2, and that's true in a parallel circuit, so I'll put a P. I'm going to come up here and write 1 over R equivalent will be what 1 over R1 is. That's 1 over 3 ohms plus 1 over 6 ohms. Now we have a teeny tiny problem, not to panic. We have different denominators, 3 and 6, so we need to find a common multiple. If we make that 6 ohms, something over 6 ohms is 1 over 3, and the answer is 2 over 6 ohms. So we can express 1/3 as 2 over 6, and now I'll rewrite 1 over the equivalent resistance will be equal to 2 over 6 ohms plus 1 over 6 ohms. So 1 over the equivalent resistance will be 3 over 6 ohms. So add the numerators, keep the denominator the same, and then to solve this, we're not done. The resistance is not 1/2 or 3 over 6 ohms. You take the reciprocal, the equivalent resistance over 1, so you flip this, is equal to 6 ohms over 3. Whatever you do to one side, you do to the other. And that total resistance ends up being 2 ohms. So it's interesting. You get big resistances that give you a small total resistance. So the total resistance for this problem, running out of room, 2 ohms. What is the voltage in any spot? This is an easy one. If I come up 18 through R1, down 18. So this voltage for R1 or V1 is 18 volts. Let's find our other favorite color, that pink. That works. If I come up 18, I'm going to come down through 18 and bring it back home. So again, V2 is 18 volts, and we remember that V is V1 is equal to V2. So the answer is 18 volts. Let's move on. So what is the current through R1? We're going to apply Ohm's law to do this. You know I is V over R. So I1 will be V1 over R1. If I put a subscript anywhere, I do the same thing on the opposite side. What is V1? As we stated previously, that's 18 volts. You can rewind and look at that. Divided by R1 is 3 ohms. 18 divided by 3 is 6 amps. So that current going right there will be 6 amps. Can you predict if this resistance is twice as large, but you're still applying 18 volts across that, what would the current in this branch be, more or less? More resistance means, that's right, less current. Let's carry it forward. What is the current through R2? Remember, this is 18 volts, so I2 is V2 over R2. V2 is still 18 volts because that's the king, divided by R2, 6 ohms, and you get 3 amps. So in the previous problem, we had 6 amps of current through that 3 ohm branch, small resistance, large current. Here we have 6 ohms of resistance and 3 amps of current. Double the resistance, you half the current. What is the power used by R1? Now we know the voltage is 18 volts, and we know the current is 6 amps there. And here we know the voltage is 18 volts and the current was 3 amps. So you could use, there are several ways to do this. One is power is I times V. So finding the power for 1, it's I1 times V1. So power 1 is I1, which happens to be 6 amps, times V1, 18 volts. You're going to get an answer. Use your computer, give it a shot. Another way to do this, power 1 is I1 quantity squared times R1. Give it a shot. Power 1 equals the current in that branch, 6 amps quantity squared, times R1 is 3 ohms. Should you get the same answer? Give it a shot. Use your computer. And then another way to do it, power 1 is V squared over R. So these are all equations that we used previously to find power. Again, I'll give you a cheat sheet. So that is 18 volts squared divided by what that resistance is, 3 ohms. Should you get the same answer using equation A, B, and C? Give it a try and see. Let's reveal the answer and see what they have to say and see what method they used. So again, they used power 1 is I1 times V1. 6 amps times 18 volts, they're going to get 108 watts. That means 108 joules of energy is transformed every second. What is the power from R2? So let's go back. So we said 108 watts there. Now what's king here? Let's think about this. What value is king? And the answer is voltage is king. So power is V squared over R. So since these have the same voltage, voltage has no effect on power. The one with the greatest resistance will have a smaller power output because as R goes up in the denominator here, power goes down. So let's just reference 108 watts. If we double resistance, we should half power. Let's give it a shot. Power is V squared, or power for 2 is V2 squared over R2. So it's 18 volts, because voltage is still king, squared, divided by R2 is going to be 6 ohms. Let's reveal the answer. Again, before we had 108 watts, now we've doubled the resistance. Half 108 is 54. Beautiful. So we'll move on. Let's solve this last example for circuits, and then I'll give you a nice cheat sheet. Solving quickly, finding the equivalent resistance, use the 1 over EQ, where the total resistance is 1 over R1 plus 1 over R2. So I'll highlight this, and I'm going to dupe it, bring it down so we can use it again. We'll cheat. Solving for this, 1 over REQ, sorry about that, is 1 over 3 ohms plus 1 over 9 ohms. So we need common denominator. We need 9 ohms in both cases. 1 over 3 is 3 over 9, so we'll cancel. So the total resistance is, or 1 over the total resistance, is 4 over 9 ohms. 9 over 4 is a little more than 2 ohms when we take the reciprocal. 2.25 ohms again. So again, to solve for that total resistance, you have to take the reciprocal of both sides of this and then do the math. Pull out your calculator and give it a shot. You'll get 2.25 ohms. Relatively small resistance. What is the voltage in any spot? Since V is V1 is equal to V2, if we put 9 volts up, we get 9 volts there. If we put 9 volts up, we'll get 9 volts there. Voltage is king. 9 volts is the answer. What is the current through R1? Oh, this is great. It becomes very easy. You know we have 9 volts there. We have 9 volts there. Now let's take a look. You have 3 ohms versus 9 ohms. Which gets more current? The answer is the one with less resistance, 3 ohms. If this gets a certain amount of current, this will get 1/3. More on that in a minute. So what is the current through R1? That's I1, and that's V1 over R1. V1 is 9 volts, divided by R1 is 3 ohms. You get 3 amps of current in that branch right there. You also get current there. We'll do that next. But let's go back and reveal the answer. Little feedback, 3 amps. What is the current through R2? We still know that the voltage across R2 is 9 volts because you come up 9, you come down through 9. So I2 is V2 over R2. I2 will be V2, 9 volts, over 9 ohms. You get 1 amp. So if we go back, you get 3 amps in the top one, and 1 amp in the bottom one. You get triple the resistance, you get 1/3 of the current. So we go from 3 ohms to 9 ohms. We've tripled the resistance, we have to third the current to keep the voltage the same. What is the power used by R1? Easy way is just to use power for 1 is current for 1 times voltage for 1. So power for 1 is the voltage, or rather the current for 1. That was 3 amps times the voltage for 1. That was 9 volts. Power for 1 will be 27 watts. Power for 2, and we're in the home stretch here, P2 is I2 times V2. I2 was 1 amp, we stated, times what V2 is, 9 volts. Power 2 is 9 watts. 9 joules come out every second. Whoa, we made a mistake. We made a mistake somewhere. Let's just double check our math here. Is I2 9 amps? That's not right. Let's double check our math. Pardon me. We come up 9, we came down 9 volts. So we have 9 over 9, that's 1 amp. That should be a 1. 1 times 9 is not going to be 81. It's 9 watts. We'll have to correct that one. Make a note. Alright, let's make a nice little cheat sheet for everybody that you can use when you're solving circuit problems. Whenever you're dealing with a series circuit, we know that current is king, first of all. So current anywhere in the circuit would be equal to the current to the first resistor, equal to the current in the second resistor. and voltage would be equal to the sum of the voltage drops across the individual resistors. And then third, the equivalent resistance is R1 plus R2. Now if you had a third resistor, you say equal I3 plus V3 plus R3. But again, we'll just do this assuming you have two resistors. In a parallel circuit, we know that I equals I1 plus I2, V equals V1 equals V2, and 1 over the equivalent resistance is 1 over R1 plus 1 over R2. And another way to write this, R equivalent would be R1 plus R2 to the negative 1 power. Stick to whatever method works for you. So I'm going to box these in. And we have generic equations. Again, current is king for a series, and voltage is king for parallel. Now we'll come down, I'm going to write Ohm's law three ways, have it your way. I is V over R, V is I times R, and R is V over I. So just solving that for different equations. And then another tool for the toolbox are the power equations. I'll just make them in red. Power can be calculated by taking the product of current and voltage, or it could be I squared times R, or it could be V squared over R. So this is the handy dandy sheet that you can refer to. You can jot this stuff down, print it, whichever you prefer, screen save it, and come back, and you'll use this when you're solving your circuit problems. Good luck with your studies. Keep up the great work, and we are pulling for you.